Hello and welcome back to Algorithmic Game Theory. Today we'll continue and complete our discussion of inefficiency due to strategic behavior. I hope you remember that last time we introduced the price of anarchy, which was one way to bound the loss due to strategic behavior. This is taking a somewhat pessimistic view as we say, well, how much worse is the worst equilibrium compared to the social optimum? Today, in the first part, we'll take a more optimistic view by considering the so-called price of stability, which compares not the worst equilibrium, but the best equilibrium to the social optimum. And then in the second part, we'll again come back to the price of anarchy, but then we'll consider a payoff maximization game rather than a cost minimization game. And we'll see to what extent, techniques are similar or different there. But let's first start with the discussion of the price of stability, and we'll do this in the context of cost-sharing games, which are a special case of congestion games. So let's formally define these. So what is a cost-sharing game? A cost-sharing game is nothing but a congestion game in which delays have a certain form, namely a cost-sharing game is a congestion game where all delay functions have the form dr of x is equal to cr divided by x for constants cr. What does this mean? Well, this means that there is this one cost CR for resource R, and the players that use this resource split up the cost of this resource evenly. So how do we then get to the social cost of a state in this setting? Well, just as usual, or as also as last lecture, we'd say that the social cost is the sum of all players' costs. Now, in this congestion game, we see that, a player's cost, as in any congestion game, is the sum of the delay values. But if we now rearrange this sum, then we see, okay, maybe let's first take a step in between and let's see, okay, dr of nr of s, this is certainly cr divided by nr of s. And how often do we get this term? Well, we get it exactly nr times. So, an alternative way of writing this is to say, okay, take the sum over all resources that are used by at least one player and just sum up the CR values. Good. So what we want to do is we want to bound the social cost of a pure Nash equilibrium in such a cost-sharing game. Well, unfortunately, the price of anarchy is really, really bad. Let's see this in a simple example, namely the following. We have one source, one sink, and then we now have 1 plus epsilon as the cost for the top edge, and we'll have a cost of n for the bottom edge. So these things that I'm drawing here, this is the CR value. Good. What is a pure Nash equilibrium in this setting? Well, one pure Nash equilibrium would be, we'll have n players. So one pure Nash equilibrium would be that all players take the top edge. And this is also the social optimum. What would be the social cost then? This would be 1 plus epsilon. Okay, but there is another pure Nash equilibrium. Namely that all players take the bottom edge. And what's the social cost then? Well, it is certainly just n. Why is this also a pure Nash equilibrium? Well, if one player now unilaterally deviated, what would his or her cost change to? So right now all n players are using this bottom edge. They're sharing the cost of n, which means each of them will have a cost of 1. We'll have a delay of 1. Now, if I moved to the top edge, if I were the only player to move to the top edge and all other players are still on the bottom edge, well, then I'll have a cost of 1 plus epsilon. I have nobody to share this with. So my cost will be 1 plus epsilon, whereas down here my cost was only 1. So for me individually, this feels to be better to now stay here in this, okay, admittedly really bad equilibrium, because for society, this is now cost of n, whereas if we were all using the top edge, this would even be an equilibrium, then we would society would only have cost of 1 plus epsilon. And for each of us individually, this would also be better, because only the cost of every individual would be 1 plus epsilon over n. Nonetheless, I think you may know many situations in which actually kind of society is playing this bad equilibrium, because, well, you don't want to be the only one who does something different, because your individual cost would be much higher than if you just do whatever everybody else does. For example, the way you can think about this is those are two kinds of technology, and now there is the much better technology and the worse technology. But somehow, for some reason, maybe because they're earlier in the market, everybody uses the worse technology. And then suddenly, well, you cannot just individually use the better technology because it might be incompatible. Maybe you wouldn't want to use other power plugs, although they might be a lot better than what everybody else is using. And eventually everybody would be happier if we all use different power plugs or USB plugs or whatsoever. But this is not how it works, because we are kind of stuck in this bottom, in this equilibrium here at the bottom. So nonetheless, we see that the price of anarchy only gives us only a very limited perspective. Namely, it tells us, well, the worst thing that can happen is actually happening. What we'll ask today is, well, here in this setting, it is not necessary. So there is also good equilibrium. Namely, this is the social optimum and it is an equilibrium. And that's the question that we will ask today. How much efficiency do we have to lose by considering strategic behavior? So what is the best of our equilibria? What is the social cost of the best of these equilibria? And this is called the price of stability. So to define the price of stability, we do this exactly the same way as for the price of anarchy. So for an equilibrium concept, EQ define the price of stability by, this is now POS subscript EQ, take the minimum cost, the minimum social cost of any equilibrium, and compare this to the minimum social cost of any state in your game. So last time we saw that the price of stability for coarse correlated equilibria might be higher than for correlated equilibria, and this might again be higher than for mixed Nash equilibria, and vice and so on. Here now the story is a little different, because we're always considering the best of these equilibria. So the price of stability for coarse correlated equilibria can only be smaller than the one for correlated equilibria, and so on. So if we write this down, then we see, okay, this is always, of course, at least 1, but then the price of stability for coarse correlated equilibria is at most the price of stability for correlated equilibria, is at most the price of stability for mixed Nash equilibria, is at most the price of stability for pure Nash equilibria, and this then is again at most the price of anarchy for pure Nash equilibria, and so on. Because, well, the best pure Nash equilibrium is still, can only be better than the worst pure Nash equilibrium, but the best pure Nash equilibrium is also a correlated equilibrium or a coarse correlated equilibrium, and so on. So there can only be better equilibria in this sense. What is of course a little different here than if we talk about the price of anarchy is that here it might happen that equilibria do not exist. Well, this can also happen for the price of anarchy, but then kind of we don't care. Whereas here, bounding the price of stability implicitly also means that you have to show that an equilibrium exists. Because, well, somehow you have to say, okay, there is an equilibrium, first of all, and this equilibrium has to have only cost this and this high. So that's why oftentimes it's actually more difficult to bound the price of stability than the price of anarchy. But still, we can do this now for these cost-sharing games. And let's first start with symmetric cost-sharing games. We will show that in a symmetric cost-sharing game, so all players have the same set of strategies. The price of stability for pure Nash equilibrium is 1. So this means there is always a pure Nash equilibrium which is at the same time a social optimum. Or you can also say this, there is always a social optimum which is also a pure Nash equilibrium. We've seen in our example before, let me go back to this example. Here we've seen that there were actually 2 Nash equilibria, and one of these was a social optimum. And indeed, this is a symmetric cost-sharing game, so this is actually a special case of our theorem. We claim that whenever all players have the same strategies, then there is a pure Nash equilibrium which is also socially optimal, or one of the social optima is also a pure Nash equilibrium. So how do we prove that? Well, we just now explicitly construct this pure Nash equilibrium. It is even a symmetric equilibrium, which means that all players use the same strategy. How do we do that? Well, set S1, so the strategy for player 1, to the strategy from sigma 1 that minimizes the sum of the costs. So if there were only if there were no other players except for player 1, then what would player 1 do? And then we let just every player, also the other players, we let them do exactly the same thing. Now, why is this socially optimal, and why is this a pure Nash equilibrium? Well, let's just see the social cost, an individual player's cost after deviating. So how would we get this? Well, we would now take the sum over all resources that this player is using now, And so we would now be taking the cost after deviating would be the following. We would have here as the first part, we would have the costs of the delays of the resources that the player was using before and afterwards. And of course, all players are using this resource, so the cost will be divided by n, because they equally share the cost. And then there might be some other resources that the player is now deviating to, but he's the only one using these resources. That's why, well, he cannot share the cost with anybody else. But this now means that this will be at least 1 over n times the cost that this player incurs, or 1 over n times the sum of the costs of the resources that this player is now using. Okay, I hope that's kind of clear. This, of course, is at least the cost, the sum of the costs of Si rather than Si prime. Why is this? Because we set Si to be the strategy that minimizes the sum of the CR. And this is exactly 1 over n times the cost that the player had when only using strategy Si. So this is certainly a pure Nash equilibrium. And why is it a social optimum? Well, this is a social optimum because even player 1 couldn't have done something else, couldn't have a smaller cost if there were only player 1, and the other players cannot make this any cheaper. So what we saw is that there is always a social optimum, which is also a pure Nash equilibrium. With a little bit of more work, you could even show that every social optimum is always a pure Nash equilibrium. But we very explicitly used the symmetry of the game. Where did we use it? Well, exactly here, because we just set all strategies of all players to the same. What now if we cannot do this? So if players have different strategies, well, then the price of stability is greater than 1. Let's see this first in an example. We'll now have n players, and each of the players has a different source, and they all have the same sink. Player 1 can go there via a direct edge that has a cost of 1. Player 2 via an edge that has cost a half. Player 3 via an edge that has costs a third, and player n via an edge that has costs 1 over n. Okay. What's now the alternative? The alternative is an indirect way of getting there. Well, they can all take an indirect way. For free, they can actually get to this node V. And from this node V, there is an edge taking them to the top at cost 1 plus epsilon. First of all, what's the social optimum here? Well, the social optimum is pretty obvious. Recall that the social cost is the sum of the cost of the resources that somebody is using. And here now we can do with 0 plus 1 plus epsilon, because all players can first go down to V and then use the 1 plus epsilon edge to get to T. So this means each of them will have an individual cost of 1 plus epsilon over n, and all of them together have a cost of 1 plus epsilon. But is this an equilibrium? No, it isn't. Because, unfortunately, there is this player n who says, okay, I'll have a cost of 1 plus epsilon over n via this, if I do this thing that everybody does. But if I now individually deviate, then I'll have only a cost of 1 over n. Okay. So, is that then in an equilibrium? If only player n uses his or her private edge, and the others still use this public edge. No, it isn't, because then the shared cost is only 1 plus epsilon over n minus 1. So then player n minus 1 would say, okay, why would I use why wouldn't I use my private edge? So what you can actually see here is that there is only one pure Nash equilibrium, namely everybody uses his or her private edge. So the only pure Nash equilibrium is to use these direct edges. And what's the social cost? This is, well, 1 plus a half plus a third plus up to 1 over n. This is the nth harmonic number, which grows proportional to log n. Whereas the social optimum would be a cost of 1. 1 plus epsilon. So this means that the price of stability for pure Nash equilibria will be at least the nth harmonic number divided by 1 plus epsilon. But fortunately, we can also derive this as an upper bound on the price of stability. Let's see this. The price of stability for pure Nash equilibria fair cost-sharing games. Is at most the nth harmonic number if we have n players. So how do we prove such a theorem? Well, I hope you remember that pure Nash equilibria are exactly, in a congestion game, the local minima of the Rosenthal potential. And what we'll do now is we'll compare the Rosenthal potential to the social cost. Don't forget that these are two different things. The Rosenthal potential had no particular meaning in terms of the sum of the players' cost. It was only like a tool that we used to show that pure Nash equilibria exist, for example. And this was the thing that reduced with every improvement step. Whereas the social cost, that's something different. This is the sum of the players' cost that we're trying to bound now. Let's see these differences. So the Rosenthal potential of a state S is how big? This is what we write by phi of S. And what we do is we take the sum over all resources, and then we add up from 1 to the number of players using this resource, and then we take the cost. We generally take the delay function evaluated at I, which in this case is the cost of the resource divided by I. And what we'll want to compare this to is the social cost of S. For this, we derived here that we would take the sum over all resources, which at least some player uses, and we just add up the cost of this resource. How can we get from one to the other? Well, let's see. The Rosenthal potential we can now very clearly bound as follows. Take the sum over all resources that at least some player is using. Well, because we don't care about the other resources, they don't have any terms contributing to the sum. And then we'll have 1 plus a half plus a third, and so on, up to 1 over nr of S. And this here, this is clearly at most, take the sum over all resources that some player is using, CR times the nth harmonic number. And so this would be the nth harmonic number times the social cost of S. So the Rosenthal potential is at most the nth harmonic number times the social cost of the state. How does this help us? Well, what else can we see? We can also see that the Rosenthal potential is at least the social cost of the state. because, well, just leave out every term except for the first one. So this will be at least the sum, the cost of the resources that at least some player is using. And this will be the social cost of S. So this means that for any state S, the Rosenthal potential is at least the social cost of this state, but at most Hn times the social cost of this state. Now take a state that minimizes the Rosenthal potential. Take a global minimum of the Rosenthal potential. What do we know about this? Let's call this S. Then clearly we know that S is a pure Nash equilibrium. Because, well, every local optimum of the Rosenthal potential is a pure Nash equilibrium, so also a global minimum of the Rosenthal potential is a pure Nash equilibrium. Now consider a social optimum. S star. What do we know? Well, we know that the Rosenthal potential of S will be at most the Rosenthal potential of S star. But what else do we know? That the Rosenthal potential of S will be at least the social cost of S. And also the Rosenthal potential of S star, this will be at most Hn times the social cost of S star, because these were the two things that we've just shown. Now if we plug all of this together, then we see that the social cost of S is at most Hn times the social cost of S star, or in other words, that the social cost of S divided by the social cost of S star is at most the nth harmonic number. So we found our pure Nash equilibrium, not this explicitly as we did this before, but well, also in a pretty easy way that we've seen before, namely take a global minimum of the Rosenthal potential. We know that this is a pure Nash equilibrium, and then we just do this comparison of the social cost via the Rosenthal potential. Once again, these are two different things. These are not the same, but we can, for these games here, we can use one as an upper bound for the other. For other congestion games, this will generally not work. This will give you much worse guarantees, which are actually useless. And what we've also seen is that we cannot actually do better. Hn, the nth harmonic number, this is actually the best that we can prove here, because we had this equilibrium, we had this game in which we saw that the best equilibrium is no better than Hn times the social optimum. So now we've understood pretty well the price of anarchy and price of stability of these cost-sharing games, and now we'll turn to market-sharing games, which are, well, almost the same, except for now you're not trying to minimize your cost, but you're trying to, well, maximize your market share, which means that this will be a payoff maximization game as opposed to a cost minimization game. For the very basic things like existence of equilibria and so on, this doesn't make any difference. But for the price of stability and price of anarchy, this makes a big difference, because suddenly we are now relating, or suddenly now large numbers are better than small numbers. But let's first define these market sharing games. In such a market sharing game, we have n firms or players, and we have m markets, m. And each firm can decide to invest in one of the markets. We say this by writing Si is a subset of M, where for any player I. So I realized that notation is now a little different, because suddenly capital Si is the strategy space for player I. Whereas before, capital Si was the strategy choice of player I. Now small si will be the strategy of player I. This always depends on whether you, what notation you choose always depends on what you actually want to express. And somehow it turns out that whenever you use congestion games, it is more convenient to use these capital letters, because you explicitly want to say that these are sets, whereas here those aren't sets. Here your strategy is just one market that you invest in, and the set of possible markets is a subset of all markets. Good. Now every market has a demand. And if multiple firms now invest in the same market, then the market demand is shared equally. So what is the payoff or the utility of a player in a state? We write this as ui of s is equal to v subscript si divided by n subscript si of s, where nj of s, that's still the number of players using a resource, or in this case, investing in market J. So once again, what does this mean? Well, if you are player I, you are now choosing one market SI. And then there is the total demand V of SI in that market. And we now divide this by the number of players who are investing in this market. This is N subscript SI. Why that? Because you are investing in market SI of S. And NJ of S, that's just the number of players investing in market J. Now we don't want to bound the social cost, but the social welfare. The social welfare of some state S this is nothing but the sum of all players' payoffs or utilities in this state. And just as we saw this in the case of our cost sharing games, we will now take just the sum of all markets that somebody is investing in, and then we take the demand of that market. Or, now given the notation here, we could also write this in a different way. Take the set of markets that is invested in and take a sum over all these. What is a little hidden in this notation here is that there might be repetitions in this set, but then you're actually taking the sum, having this in the sum only once. So if everybody's investing, for example, in market 1, then all of S1 through Sn, those are all equal to 1, and then this sum would be only V1. This is maybe more explicit in this term here. Let's see this happening in an example. Let's have n markets. Each player can invest in every market. And what are our demands? Well, the first market, that actually is very promising because we have a demand of n plus 1, whereas all other markets only have a demand of 1. What is the social optimum? How do we maximize the social welfare? Well, we would maximize the social welfare if each player invested in a different market. That's always the best thing that you can do here, that players just invest in different markets. So the social optimum would be all players in different markets and we'll have a social welfare of n plus epsilon plus n times 1. So this will be 2n minus 1 plus epsilon. But what's the only pure Nash equilibrium here? Well, the only pure Nash equilibrium this will be that all players invest in the first market. Why that? Because even if everybody's investing in the first market, then you still get a utility of n plus epsilon over n by going to this market. Whereas for any other market, you would get only 1, which is strictly less. So you definitely want to go to the first market, regardless of what the other players are doing. And what's the social welfare? The social welfare is only n plus epsilon. Good. So as we see, we kind of, again, lose welfare because players are strategic. Because we cannot tell the players which market to invest in, but it is up to their choice. And we'll have, again, the question of how big will the price of anarchy be? Or you could also ask the question about the price of stability, but as we see here, the price of stability might actually be already somewhat large, at least it will not be 1, and eventually what we will see is that even the price of anarchy is bounded by 2 here. But before we do this, let's first talk about existence of equilibria. Why are there always pure Nash equilibria in this game? Well, because we can rewrite these games to be congestion games where actually the players want to minimize something. Namely, we could set the delays to negative numbers. So it would be minus market demand divided by number of players in this market. This would be a delay. And then if you do all this, then you see, okay, in this congestion game with negative costs, then your in this congestion game with negative costs, so we will still have to argue that there are always pure Nash equilibria. And let's just write this down as an observation. Every market sharing game has a pure Nash equilibrium. Why is this true? Well, one way you can show this is you can actually see that these market sharing games are also congestion games. Well, they are even almost cost sharing games, except for that now we want to model by these costs, we actually want to model the player's utilities, and we would do this by negative costs. So we would now say, okay, the delay, or first of all, the resources are the markets, and the delays of markets are minus market share divided by number of players in that market. And then you see, okay, actually, every pure Nash equilibrium of this congestion game is exactly also a pure Nash equilibrium of this game, and vice versa, just because we actually model the same thing. We model the same preferences. But one thing is different, namely the way we think about this social welfare these are now positive numbers. And the way we do these comparisons, this is actually a lot different. Because suddenly we want to maximize things and we kind of take ratios of social welfare. So that will be something different. And let's now talk about the price of anarchy in these market sharing games. So how do we define the price of anarchy in a utility maximization game? Well, we just do it exactly the same way as we define it in cost minimization games, except for some details, because now we're swapping minima and maxima. So let's write this down formally. Given a utility maximization game, let EQ be again a set of probability distributions over the states. And for any such probability distribution, we write social welfare of P as the expected social welfare if you draw a state from this distribution and then take the social welfare of the state that you've just drawn. Or alternatively, you can again take the sum over all states, take the probability that you play this state, and then the social welfare of the state. And now we can define the price of anarchy. For equilibrium concept EQ, we say that this is PUA subscript EQ. And what was this before? Well, before this was the worst social cost of an equilibrium divided by the best social cost of any state. Now, well, everything is reversed because we now say, okay, take the best social welfare and compare it to the worst social welfare of any equilibrium. Why do we now have the social optimum in the numerator? Well, the idea is simple because we want that this ratio is always bigger than 1. And this way, larger numbers are worse, smaller numbers are better. So again, the price of anarchy will be at least 1, and the smaller it is, the better it is. And let's now talk about smoothness in the context of utility maximization games. Well, this is also a little different. I hope you remember the definition of smoothness for a cost minimization game. and then you see that this is a little different. We now say that a utility maximization game is called lambda mu smooth, where lambda is bigger than 0 and mu is non-negative if for every pair of states S and S star the sum of utilities, if one player deviates to S star, the others keep playing according to S, and this is at least lambda times the social welfare of S star minus mu times the social welfare of S. So again, we are considering here this entangled sum where, well, we always let one player deviate to S star, the other players keep playing what they are, and then, well, before we had that this is at most lambda times social cost plus mu times social cost. Now it is a little different because, well, first of all, this should be at least because, well, we're trying to lower bound the social welfare and not upper bound the social cost. And also what is important is that now here we're subtracting the social welfare of S. So this only makes it easier to make sure that this condition is fulfilled. And still, by exactly the same way as we did it last time, we can show that smoothness implies a bound on the price of anarchy. Let's see this once again so that you don't forget how this works. In a lambda mu smooth game, and by this I now mean a utility maximization game, the price of anarchy for coarse correlated equilibria is at most 1 plus mu over lambda. So the term that we're getting is a little different than last time, but everything else is kind of the same kind of a statement. So let's see how we can prove this. Let's only do the proof for pure Nash equilibria. If you want to do this for coarse correlated equilibria, have a look at what we did last time and see that we can actually, what we're doing now can be easily combined with the ideas that we did last time. So we now let S be a pure Nash equilibrium. S star be a social optimum. Okay, so just as we had this before, like every price of anarchy proof will something look like this. Now what do we have to bound? We will have to bound the social welfare of S. Well, this is nothing but the sum of all players' utilities. Now, because we are in an equilibrium, we can say, okay, no player can benefit from unilaterally deviating to S star. And now we use the smoothness bound. We say, okay, this is at least lambda times the social welfare of S star minus mu times the social welfare of S. And if we now combine this, then we see that 1 plus mu times the social welfare of S is at least lambda times the social welfare of S star, or in other words, that the social welfare of S star divided by the social welfare of S is at most 1 plus mu divided by lambda. So I hope this looks familiar, because this is exactly the kind of proof that we also did last time. Now the signs are a bit flipped, but everything else is just the same. So if we now want to understand the price of anarchy of these of these market sharing games, then all we have to do is to show smoothness. So this is what the only thing that remains for now. What we claim is the following. We claim that every market sharing game is 1,1 smooth. So what kind of a bound does this give us? Well, so we'll have lambda is equal to 1 and mu is equal to 1. So what does this mean? This means that the price of anarchy for coarse correlated equilibria, this is no worse than 1 plus mu divided by lambda, so this will be at most 2, the price of anarchy. Okay, cool. Let's see how we can prove this. Well, all we have to now understand is what these ui of si star, s minus I terms look like. Well, this is nothing but the market share, the demand in market SI divided by how many players use this market in Si star, S minus I. But how big is this? Well, this is, how big can this be? Well, this is clearly at most 0, because we assume that these V's are non-negative. But it may also happen that no player was using this particular market before, was investing in this particular market before, in which case this is V subscript Si star. And this is true if no other player is investing in that market. Good. And indeed, we can say, okay, we can even derive a more coarse lower bound for this. Well, still this will be non-negative, but we can say, okay, we only say that this is V subscript SI star if SI star, if this market was never invested in by anybody in S, nor by the players that have a smaller index in SI star. Well, this is true because this second set that we have here, this is just a superset of the previous set. Okay. So this now helps us as follows. If we now let capital T be the markets that somebody invests in S, and T star, if this is the set of markets that somebody is investing in S star. What is now the social welfare, or what is this entangled sum? What's a lower bound for this? Well, we can clearly say this is at least the sum of all j in T star take away T Vj. Why is this? Because if we take the sum over all these terms, then, well, the ones that are in T, the markets that are in T, those never occur. But then there are the ones that are in T star, and for those we get the V value exactly once. Namely, consider what player 1 is doing in S star. Well, maybe this is something that was also done in S, then we're not getting anything from this. But it might be that this is something new. And in this case, this actually contributes to this sum here. But then this precise market won't ever contribute anything, but so even if player 2 is now using that same market. But what we get is that if we take the sum, then every market that is in T star but not in T will appear exactly once in this sum. This is just a standard telescoping sum argument, actually. So what is this? Well, this is nothing but take the sum over all markets that are in T star or in T and add up the Vj values and then subtract everything again that is in T. Okay. How big are these things? Well, we see that this second sum here, this is at least the sum of all T star, V and T star, Vj, and this is exactly equal to, yes, I'm writing down now the exact same thing, I realize. And what do these things mean? Well, the first thing, that's the social welfare of S star, and the second thing, that's the social welfare of S. So in combination, all of this is at least 1 times the social welfare of S star minus 1 times the social welfare of S. And this is exactly what we required for smoothness. So this now wraps up today's lecture. We've now seen these cost minimization games, how we could bound the price of anarchy and the price of stability there. With the price of anarchy, we bounded last time via smoothness. Today we bounded the price of stability, and for our special class of congestion games, which were cost-sharing games, we used this technique using the Rosenthal potential. And then in the second part, we saw how these techniques can also be applied to utility maximization games, that there is an analogous definition of smoothness. And for this definition of smoothness, well, we could, on the one hand, bound the price of anarchy, and then, on the other hand, we could prove that these market-sharing games, which are very similar to the cost-sharing games, that they are smooth in this sense. And actually, what is maybe interesting here is that we can, in this in the cost minimization world, we had no chance of bounding the price of anarchy, whereas in the utility maximization world, although it is kind of the same example, we suddenly can indeed bound the price of anarchy by only a constant, namely 2. So this concludes our overall discussion of game theory in the classical sense. Next time we will start discussing a very different topic, namely mechanism design, and then our goal will be to actually set the rules of the game rather than only observing what is happening. And this we will then actually do for the rest of this semester. So I hope you stay tuned and hope to see you next time. Thanks for watching this video today. Bye.